Alright, so in this video, I'm gonna be explaining another important article with the title Advanced Graph Clustering Methods, a Comprehensive and In-Depth Analysis. So this paper in 2024 is very important. Graph clustering, which aims to divide a graph into several homogeneous groups, is a critical area of study with applications that span various fields such as social network analysis, bioinformatics, and image segmentation. This paper explores both traditional and more recent approaches to graph clustering. Firstly, key concepts and definitions in graph theory are introduced. The background section covers essential topics including graph Laplacian, and the integration of deep learning in graph analysis. The paper then delves into traditional clustering methods, including spectral clustering and the Leiden algorithm. So graph clustering has been extensively researched for several decades. So clustering a graph is just the process of finding the optimal partition. C1, C2, C3, and so on, such that there is no intersection and the union of all of them covers all the vertices of your graph. The most forward metric is accuracy. It takes values in 0, 1 for clustering evaluation, so we use it for supervised learning with this formula. So we have a ground truth label and the predicted labels and the number of nodes. However, an issue arises when the use of accuracy of unsupervised learning. In fact, there is no association between real class labels and the clustering output. For example, a ground truth vector and a clustering result would give an accuracy of 0. While being correct. To solve this problem, this reference uses permutations of the clustering labels to find the maximum accuracy achieved with the formula. So it is better to write like this: the maximum overall permutations of what is achieved. This is more accurate. And then they talk about normalized mutual information, which takes values in 0 and 1 and should be maximized. It is specifically designed for clustering evaluation and measures the similarity between the truth label and the predicted clusters. NMI evaluates similarity at the level of clusters. It considers how well the groups formed by the clustering algorithm corresponding to the true groups in the data. So this NMI, you see the Y is the ground truth, Y hat is the clustering labels, and I is the mutual information. Here H is the entropy. So we can calculate the mutual information like this. But this P is a joint probability, and the individual are just the marginal probability. So you know the definition of entropy. The cut-score metric is a metric when used ground truth labels are not provided. Graph clustering can be performed by minimizing the cut-score. Conductance is also important in graph theory, especially in spectral graph theory. So you should be familiar with this measure. Also modularity, if you go to community detection, in their network they talk about community modularity. They don't talk about cut. They talk about modularity. And of course, you can always add these two objectives to have a better training. because there is a paper called Demon, I think, that outperforms min-cut algorithms for large graphs. So why not summing these two objectives? Because they are clustering in different, they look at the problem of clustering from different angles. So if you combine them, then you may have a better training. Because the papers in Demon, they claim that the min-cut has a hard time for training big graphs. So these are important properties of normalized Laplacian. So the second smallest eigenvalue is here. It can be formulated as an optimization using min-max Courant-Fisher theorem. And L is the Laplacian. So calculating X transpose Lx reveals this. This relationship, also known as Rayleigh theorem, is crucial because it provides a way to express the optimization problem in terms of graphs' edges. To minimize X transpose Lx, the values are assigned to the nodes such that the sum of squared differences is minimized. So in order to minimize this, the number of edges between different clusters should be minimized. So given an input graph and number of fixed class clusters K, then we want to have a cluster assignment. So we compute the normalized Laplacian, compute first K eigenvectors. This is problematic for large graphs. So this paper is not practical for large graphs. Consider the matrix with the vectors as column, and then here they say that let y sub I be the vector corresponding to the ith row. For each y sub I, group the points. So it's very classical algorithm. And you see, this idea has been for a long time. For a long time, mathematicians knew about this idea. And another model is the stochastic block model. There are a couple of papers on this, but it's very theoretical, and I haven't seen that in practical algorithms. You can use it as a likelihood function for stochastic block models. So you see that why the likelihood forms like this, and P is just a Bernoulli defined by the elements of B. I don't think your brain uses this kind of modeling to learn how messages should be passed to each other. Our brain is just a simulation, like Monte Carlo simulation, just passing messages, nothing more. There is no concept of likelihood or probability distribution. Everything is by statistics. So this article is not bio-inspired, but they use this simple graph autoencoder architecture. You know, the fact that people use autoencoder because this is Euclidean and we know what to do with Euclidean space. But the problem is, how about permutations of A? How about the rich topology that is in your graph? How do you model the substructures? For example, a triangle is connected to another triangle. How do you model that? Higher order structures. So this is not good. This approach, maybe it is good for images. Even for images, training such a graph autoencoder still has problems. And then we have our binary cross entropy loss. So the bad thing is they use k-means clustering at the end, because they say, okay, this z is not good enough, so we need to do k-means. And this here, because they use the encoder loss, and once the model is trained, it can be used for clustering.